Okay, fine. Okay, I welcome you for the summary session for the course Polymers, Concepts, Properties, Uses, and Sustainability. Uh, Let me share my screen. You are able to see my screen?
Yes, ma'am. Yes.
You are able to see my screen, right?
Yes.
Okay. Okay. So we'll go through. What we'll do is that we'll have brief recap of lectures of all the weeks. We'll just brush through whatever concepts that were taken up in this course. Okay. So week one lecture started with basic introduction on what are polymers. Okay, why are polymers so common? Advantages, disadvantages, and what are the advanced applications? So as you went through the course, you were able to see that polymers, they have, their dielectric behavior is there, conducting behavior is there, so they can be used in electronics, soft robotics, and all, right? And then
Yes, ma'am.
again, what are polymers? So, what is a monomer, oligomer, and diversity of polymers around us? It's not only the synthetic petrochemical based polymers we have, even our body is made up of polymers, right? From our DNA, it's polymers, right? So, this was all given an idea. And what is the architecture of the polymer? Like, what is the backbone, side group, end group, and what is the degree of polymerization, branching? So, these concepts were all introduced. And then next, the lectures were on what are the unique features. Okay, the concept of process structure and property, and how are they related. Okay, how, what is the structure property correlation, what is the property processing correlation. Okay, what is a structure and processing correlation, and what are the states of interest. Instead of direct solid and liquid states, we also have like liquid like state, solid like state, and all, right? So these were all given an introduction, and then there was an introduction on biopolymers uses. Okay, what are the common families of polymers were introduced, and what are the natural polymers available, and bio-based from natural sources. So bio-based means these may not be biodegradable, but their source is from nature, right? So that was discussed. And then uh, natural fibers were discussed. Okay, and what are the classification of biomolecules based on type and origin? Okay, they can be plant based and animal based, microorganism based, right? uh, so these were discussed. And then the property molecular weight, which is a very important, in terms of polymers, because they are large molecules and their molecular size, they play a very important role. And then effect of molecular size, length, branches, blocks in case of copolymers, or if you have a polymer blend, right? And then cross links for a cross linked polymeric system, and what is a monodisperse and polydisperse, right? So these were all given.
Yes, ma'am.
Yeah, I think someone has joined. Good evening, Revati.
Good evening.
Yeah. So we are just having a brief recap of all the week's lecture. Okay, we are just starting with the week one lectures. Okay, since this is a summary session, we'll have brief recap, and also whatever doubts you have, you can ask in this session. Okay. So then lecture 6 was on polymerization. Okay, here tacticity, chirality, for how the architecture is in case of polymers, the sequence, right? Protein sequencing, for example, branching, networking, and other architecture. And then the parameters like average molecular mass, and then molecular weight distribution. Since you have polymerization, you cannot have same molecular weight for all polymer chains. There can be a distribution. Okay, so for example, when you synthesize a polymer, polyethylene, say for example, One chain may have 10 units, another chain may have 30 units. So there is a distribution of molecular weight. Okay, and then what is the average segment length, branching density, length of branches, okay, step polymerization and polymerization in olefins. So these were all discussed. And what are polymers and its unique feature? Sustainability aspect, because this course also covered not only the concepts and properties on polymers but also how to bring in sustainability, because sustainability is a big issue with polymers, right? So, what are the nature of bondings and structure at multiple scales, right? Because it's a large molecule, you have structures at multiple scales, both time and length scales. So, how can we depolymerize? What are the thought process on decross linking? Okay, so that we can make these polymers biodegradable and it can be degraded. Okay, and degradation of macromolecules like scission of backbones, branches, cross links. Okay, activated degradation processes, right? And then questions related to sustainability like life cycle cost and degradation in holistic manner. So these were all discussed. And then the week 2 lectures, it was on simple concepts related to single macromolecule. So, renewable sources for polymers. So, what are the possible renewable sources? Right now, you have plant-based sources and animal-based sources and all, right? So, these were all discussed. And what how can what are the natural fibers and how can you use these natural fibers in composites, right? And the polymers from renewable sources like polylactic acid and polyhydroxybutyrate, which is from microorganism, right? These were all discussed. Next, polymerization, depolymerization. So, what is the polymerization method for each polymer? What is ionic polymerization? New ways to think about polymerization to make things sustainable. And then control of molecular architecture in biopolymers, right? And in vitro and in vivo polymerization. Okay, and depolymerization. These were all discussed. And then the next lecture was on physical states. As you know, it was discussed in the lectures. You don't have just solid and liquid states. It is liquid-like state, because even in liquid state there will be some elasticity, and solid state there will be some flow also, right? So some viscous behavior will be there. That is what we discussed in that was discussed in detail in viscoelasticity lectures, right? So those physical states were discussed, and then molecular interactions and what is the relevance of temperature, solvent, plasticization, right? And what are the when it comes to liquid like states, you have polymer solution, melt. Solid liquid like states, you have gels and liquid crystalline polymer. Solid like state, you have rubbery, glassy, and semi-crystalline states. Alright, and then next lecture was on application based terms, like type of polymers based on application. What is the thermoplastic, thermosets, rubbers, right? You have conducting polymers, ionic polymers, polyelectrolytes, right? Polymer charge complexes, dielectric elastomers, right? So these were all discussed. And polymer solution, dispersion, gels, polymer composite, right? So these were all discussed. Next, reuse and repurpose. So what is the linear and circular economy, ecological and carbon footprint, and reuse and carbon footprint for reduction due to recycle and reuse. So these were discussed. You are able to recollect, right? So these concepts and all, are you able to recollect that
Yeah.
some of the terminologies at
Yeah.
least? Yeah. What about you,
Yes, ma'am.
Revati? You're able to
Yeah,
recollect?
yeah.
Okay, good. Okay. And then molecular conformation. How, the lecture started with how is the conformation in case of small molecules like ethane and butane, and how conformations and multiple length scales, in case of a polymer becomes, right? And what is the role of conformation and statistical properties like your mean square end-to-end distance, distribution of end-to-end vector, orientation, how particular segment is oriented, how can you get a correlation factor, right? Persistent length. So these were all discussed. Next, the lecture was on size, mobility, and flexibility. So, ideal chain, freely rotating chain, right? Size of molecules in solution overlap concentration. What is it? Intrinsic viscosity. What is radius of gyration? Right? Molecules, how they orient under shear, and how, the orientation or conformation varies and in the presence of charge. Right? And uh, if it is a polar molecule, obviously, there will be an influence of charge, and molecule starts orienting in presence of charge, right? They start orienting, into dipoles, right? The dipole starts orienting. And what is an expanded chain model? And macromolecule as a Hookean spring. So this was discussed. Then there was a lecture on polyelectrolytes, right? And electrolytes and polyelectrolytes were discussed, and examples of polymeric systems with charges, right? Can you name any polyelectrolyte? Any of you?
P dot PSS.
P dot PSS is not a polyelectrolyte. It is a conducting polymer again.
Polyaniline.
It is again,
Conducting
they
polymer.
are all conducting polymers. So they have, uh, conjugations, alternate double bonds. In case of polymer electrolyte, for example, pectin, you can think of. You have galactronic acid unit. Since you have acid unit COOH group, they can dissociate into COO minus and H plus. So polyelectrolyte is basically that. You have naphion where you have sulfonic acid group. So this sulfonic acid gets dissociated in aqueous medium or in the respective medium as SO3 minus and H plus. Okay. So these are some examples. That's what sulfonated polymer fuel cell. So in sulfonated polymer fuel cell is what you use naphion, right? Mhm. Okay. Now next, uh, again, next is a recap of lectures of week 3. So lectures of week 3 started with molecular arrangements and states of polymers. So structures in biopolymers, right? So molecular structure of biopolymers, different structural levels. You have primary bond level, and then secondary, how they twist and orient, and then they form 3D structures. So primary, secondary, tertiary, and quaternary level of structures in case of biopolymers, right? For example, in protein you would have heard very commonly, right? Quaternary structure of protein, right? The basic amino acid sequence is your primary structure, and then they get helical, in case of, for example, in nucleic acids, you have DNA, you have double helix. So that is, double helix is a secondary structure. So these kind of things. Okay. And then there was a discussion on Cousin's hierarchical structure, polysaccharides, what is the role of polysaccharides, and pectin as an example of polysaccharide was discussed. The next lecture was on amorphous and crystalline states, from liquid to solid states, the importance of semi-crystalline polymers, right? The lamella arrangement, right? The spherulites, red crystals observed in proteins, polycrystalline states of polymers, spherulites was discussed. So these were all discussed in that lecture. Then there was a continuation lecture on amorphous and crystalline states. So the thermodynamic description of crystallization and melting. It's a first order transition and crystallization of what are the complexities involved in crystallization, right? And then the inherent kinetic factors in polymer crystallization, the rate and mixtures of polymers. Okay, the next lecture was on orientation, where there was a discussion on molecules, crystallites, domains, fibers and fillers, quantification, and orientation during processing. So these were all discussed. The next lecture was on interactions. Right, you have bonded interactions because of covalent bonds, and then non-bonded interactions like your van der Waals interactions. Right, so these were discussed, and hard sphere, square well, and Leonard Jones potential was discussed, right? And then the next lecture was on kinetics of crystallization, and then what's glass transition and melting, polymer crystallization, how structure and growth, nucleation to crystal growth, right? And then two models, Avrami model and Ozawa model was discussed, where Ozawa model is a dynamic crystallization model, right? Do you remember? Ozawa model is a dynamic crystallization model. So the temperature also keeps on reducing and the crystallization is happening simultaneously. Whereas Abrami, you have isothermal crystallization. You're able to remember, both of you?
Yeah, ma'am.
Okay.
Yeah.
Yes, I'm able to recall.
Yeah. And then the next lecture was on glass transition. So what happens in glass to rubber transition? Okay, properties in glassy state, right? So there will be a huge property changes when material changes from a glassy state to rubbery state, right? And dilutometry was discussed. Importance of glass transition was discussed. Next, week 4 lectures were on polymeric materials of different kinds. So here again there was a continuation and discussion of glass transition. So segmental relaxation, instantaneous relaxation, no relaxation, right? And then activated process, cooperative process, free volume theory, WLF equation, and Arrhenius and WLF dependence. So you have WLF dependence when the material is closer to its glass transition, right? Whereas Arrhenius dependence on properties, it happens when you when the polymer is quite away from the glass transition temperature. Okay, and then what are the other transitions, right? Beta and gamma transitions, which are basically some sub-segmental relaxation processes. Okay, this was discussed. And then what is the states in environment? This is again a sustainability based lecture. So what is the overall impact on environment? And then biogeochemical cycle, what is the role of polymer in biogeochemical cycle? How are they in water, soil and air? So these were all discussed. Next, there was a lecture discussion on liquid crystalline polymers. Okay, what is a liquid crystalline polymers, right? And then uh, you know uh, what is the free energy change, right? And then liquid crystalline polyesters was discussed. How the properties varies, significantly when it is a normal compared to a normal polyester and liquid crystalline polyester, right? And then aramid Kevlar was discussed. Next, the lecture was on, there were two lectures on copolymers. So first lecture, it was basic introduction on homopolymer and copolymer. What is the sequence distribution? You have a block copolymer, alternating copolymer, random copolymer, right? Okay. And can polyethylene be copolymer? It can be a copolymer, right? Can polyethylene be a copolymer?
No.
Yes, ma'am.
Yes, it can be a copolymer because
With the
CH2,
octene and all.
CH2, there can be some butene. Okay, so these kind of materials can also be there. You will end up in CH2, CH2 again. Okay, so polyethylene can be a copolymer. Okay, what is
And they
silicon?
also mentioned about the octene also, right?
Uh,
Butene along with octene.
Maybe I don't remember. Sorry. So I remember
It's okay.
butene. Yeah. So there can be, which have, your CH2 backbone can be a part of this, polyethylene copolymer. Okay. So it's not necessarily that you will have, it's the chain is because of only ethylene groups. Okay. Because you end up with CH2, CH2 only when you have the other, uh, alkenes also, right?
Yeah, ma'am.
Yeah. So next is control copolymerization for specific copolymer. Okay, how can you control? Okay, and reactivity ratios, right? And then copolymer related to homopolymer, and then free volume, and then how is the glass transition in case of copolymers? Okay, what is it will be a combined behavior, and then there was a discussion on block and graph copolymers. Okay, the next lecture was on next two lectures were on blends. So blends means mixtures of polymers, right? You have melt blending, solution blending, reactive blending. What are the methodologies you can use? And then miscibility in polymeric systems. Okay. Polymer solvent visibility was discussed, and then there was discussion on Gibbs free energy change due to mixing. Flory-Higgins theory was discussed. Okay, polymer blends, phase separation, right, and the critical temperature and TG of miscible polymer blends, right. So these were all discussed. Next, week 5 lectures were on microstructure in polymers. Okay, so polymeric materials microstructure. So phase separation when you have melt and crystal, and also a rich and alien region in case of polymer blends, right? And energy of crystallization or energy of mixing, and the nucleation and growth, uh, processing and microstructure, how a flow can induce changes in orientation and microstructure. Field assisted, for example, if they are able to respond to magnetic or electric field, again there will be a orientation, right. Changes if the field is there and depending on the intensity of field. Next lecture was on composite. So first there was discussion on wood, which is a natural composite of cellulose and lignin. And then uh, composite is nothing but polymers with another material. What are the size of reinforcement? Okay, loading of fiber and reinforcement versus ease of processing. Right, and there was a bit of discussion on applications of composites in aerospace, right. A national aeronautical laboratory, how they have used composites in aerospace, and there was a discussion on epoxy and bismillamide. Next was on stress strain response, right. What is this? There was discussion on stress strain curves and brittle, ductile and flexible polymers, right. Modulus, tensile strength, toughness. Okay, so these were discussed. Next lecture was on uses, which was on additives basically. So what are the additives? So there can be additives which are added for polymerization process to happen. Okay, and then something can be done for processing. For example, for having a flexible system for during processing, you may add some plasticizer so that you are able to bend and twist the polymers and all. So for performance also, certain additives can be added. Okay, some additional properties for stabilization, and there was discussion on plasticizers, flame retardants, stabilizers, and what is the impact of these additives in the environment, because these additives are small molecules. So when they come in contact with when polymers come in contact with the environment, they can diffuse into the environment, they can be leached out into the environment, which can be harmful. Okay, so these aspects were all discussed. Then blends and composites in terms of recycling and sustainability. So chemical recycling, mechanical recycling, challenges, because of the heterogeneity in polymers. For example, a simple, chips packet can have multiple layers, right. So that is actually, a challenge in recycling and also in, sustainability of these polymers, right. So polymeric materials recycled as blends and composites. How can you, incorporate, blends and composites, different polymeric, waste as blends and composites, uh, which can be recycled and reused for some purpose. So those kind of thought processes were discussed. Next, what is the physical and chemical cross-linking? Okay, types of cross-linking, and then, based on the functionality, based on polymeric backbone reactivities, based on stimulus. Okay, there can be covalent cross-linking or ionic cross-linking. Okay, what are the examples of cross-linked systems? Cross-linking in biomacromolecules. So these were all discussed in this lecture. So next, there was a discussion on mechanical properties. So different modes and properties, stretch ratio, elasticity. So linear elasticity, where Hooke's law, and elasticity is based on the secondary interaction. Energy spring, non-linear elasticity is an entropic spring. So what is a uniaxial stretching in rubber? And there were discussion of some simple models on non-linear elasticity like Mooney-Rivlin model and Neo-Hookean model. The next lecture was again on mechanical properties. So static testing, for small and large deformation. What is dynamic testing? especially on viscoelasticity of polymers. What are the advanced mechanics of polymers, like failure and fracture mechanics, fatigue, impact, temperature and strain rate effect. So, and then coarse graining, time temperature superposition. So, these were discussed. The next lectures were week 6 lectures. So, this was again on physical and chemical aging, sustainability. Okay, so aging due to different effects, chemical and physical aging. Okay, and then aging and then degradation of polyisoprene. Aging in wood, it can be due to aerobic, anaerobic destruction. And how can you identify if there are these kind of changes happening through FTIR? Because you can identify the functional group changes, especially in when there's some changes in the polymer, that can be through functional group changes, so which can be identified using FTIR. Okay, what is accelerated lifetime prediction? For example, if your polymer is going to be used for 20 years, you can't be checking for shelf life for, a service life for 20 years, but you do it at much more stringent condition. For example, if it is going to be used in hot climate, then you do the testing in hot temperature. Okay, or if the material is going to survive in kind of a acidic, then you do it in that kind of a condition and then check. So for example, in this condition, for 40 degrees it is there for 3 years, so we can say that at 25 degrees it can stay for so many years. Okay, so that kind of a prediction can be done. Okay, and then the next set of lecture was on solution properties. Okay, so what is an overlap concentration and intrinsic viscosity, theta temperature and solubility parameter. Okay, orientation, persistent length. Okay, so this was discussed. So next was on conducting polymers. So your electrical conductivity. So generally polymers are insulators, but there are polymers which can conduct because of their conjugation present. There is alternate double bond and single bond present. They can transport charges, behaving as a conducting material. So and then all polymer device. Okay. Next, the lecture was on dielectric response. What is the linear response, non-linear response? So basic introduction on some responses and complexity in case of polymers, energy storage and loss. Next, again, lecture was on dielectric response. Okay, so dielectric spectroscopy was discussed in detail, and then Debye relaxation was discussed in detail. Okay, in this lecture. Next, lecture was on plasticity. So yielding is the major phenomenon that shows your plasticity, right? Yield, strain softening, hardening, and then some models on plasticity like Eyring model and Ramberg-Osgood model were discussed. Next, polymers, properties of composites. So, how does the shape, size, and type of fillers play an important role? Okay, how are they pre-mixed for ease of processing? Right, parallel and series mixing rules, and Halpin-Sign model was discussed, and then thermal or electrical conductivity of composites, and then dilute system Maxwell model was discussed. Right, and volume fractions of fillers and how processing, so these play a role, right? These were all discussed. Week 7 lectures were on viscoelasticity in polymers. You're able to follow, right? And if you have any doubts in any lecture, we'll discuss it. Okay, please do ask because this is going to be a last session. Okay, so lecture 45 was on viscoelasticity. Okay, the concept of viscoelasticity was introduced. So, viscous response and elastic response, the molecular view. Okay, what are the contributions of this viscoelastic response? There was a discussion on Deborah number and terminal response. Okay, and then polymer samples when they are subjected to creep and recovery, how do they respond? Okay, next was on thermal response. So high temperature response for different polymers, thermal signatures. So your DSC was discussed. Okay, thermal conductivity in case of polymers was discussed. Next, characterization, viscoelasticity characterization. How can you characterize? What is the static test, dynamic test? Okay, what is the type of deformation? Samples, geometry that should be used. What are the control variables and measured variables? And there was a discussion of creep and stress relaxation. Right? Next was on viscoelasticity simple models. So what is the relaxation process and linear viscoelasticity? What is a void model and the creep response for a void model and Maxwell model and stress relaxation response for Maxwell model were discussed. Next, dynamic mechanical analysis. So your oscillatory testing and your Maxwell model and its response was discussed. There was discussion on dynamic mechanical analysis. So what are the different geometries and different fixtures, rate and frequency, stress or strain control, temperature control, how can you bring in all these aspects? And then what are the regions of viscoelasticity? There was a discussion on storage and loss modulus, right? Of viscoelasticity response. Next, damping applications. So energy dissipation during stress strain cycle, energy storage during the stress strain cycle, and then damping of vibration and sound absorption. Standard linear solid model was discussed. What are damping materials? So these were all discussed. Next lecture was on time temperature superposition. Right? So the linear viscoelasticity, the integral statement for Maxwell model, Boltzmann superposition principle was discussed, and time, frequency, temperature equivalence. Okay, shifting of data based on measured at different temperatures. Right. So you can do for a particular range of frequency, you can do for different temperatures, and then you can make a master curve. Right. So that can be done, and then impact and energy absorption, high rate of loading, energy and stress intensity, failure process, right? Fracture energy, and polycarbonate ABS blends and alloys, right? Then there was a discussion on impact strength, ISOT, Charpy test, and values for different polymers. And then testing for applications. So there are certain trade tests also. Okay, not only the research purpose test, but trade test also, which gives some numbers which are useful for industrial applications. But the same value cannot be used for a different application. For that particular application, this trade test value can be suitable. Okay, so that was discussed. Okay, for example, hardness testing was discussed. Okay, different methods of testing, volume and surface resistivity was discussed. The next lecture was on properties of blends. The glass transition for blends and then visibility, synergistic properties and additive properties in case of blends and copolymers. How do you toughen, a polymeric system using rubber particles? And then blending of conducting polymers was discussed. The next lecture was on biomimetic. What are biomimetic devices? So biomimetic polymer examples in lubrication, right? Was discussed. Uh, so here there was a discussion on synovial fluid, right? Synovial fluid has a very low friction coefficient, right? Even lower than ice. Do you remember? Any of you?
Yes, ma'am. And it contains carbohydrate. And
Yeah, good. And then can polymers be developed which can mimic materials in biological system? Here there was a good discussion on collagen. Okay, the hierarchical structure of collagen was discussed. Next lecture was on advanced mechanics. So, phenomenological description of mechanical response. What are the mechanical analogs, right? Uh, that was discussed. For example, uh, you know, your spring and dashboard. For spring is for elastic response, right? And dashboard is for viscous response, right? Sliding element for plastic response. So these are the mechanical analogs. And failure, Griffith's hypothesis, and crack growth mechanism, fatigue was discussed, right? And then there was a summary of the mechanical response also. The next lecture was on viscoelastic response examples. So, master curves. How can you produce master curves? Here there was a discussion on three complaints of polystyrene at different temperatures and master curves based on experimental measurements, dielectric response of PVA, and viscoelasticity relaxation time and different measurements. So, these were all, these examples were discussed in this lecture. Next lecture was on polymer packaging. So packaging can be for a barrier film, different applications can be a barrier film. So for example, oxygen barrier, moisture barrier, okay? They can be for impact resistance, right? your styrofoams and all, they can you can that can be filled, when you are going to transport some glass materials and all, right, so that it doesn't break. So this is for impact resistance, polymer is being used. Secondary packaging for electronic packaging. Okay, so these were discussed, and then phenomena associated with barrier films. So if you have to, have a protection from oxygen or moisture from entering, so you have to understand the diffusion, absorption, adsorption, and leaching of these small molecules in and out of polymers. Permeation, right? What are the thermodynamics of that? That was discussed. The next lecture was on porous membranes, right? So again here polymeric separation membranes. So solution diffusion, Nutson diffusion, right? Molecular sieves. Okay, these were discussed. Polymeric foams was discussed. What are the types and distribution of pores? How is it in case of polymeric foams? What are the applications? What are the blowing agents that can be used? And then examples of some polymers for foams was discussed. Next was on polymers at interfaces. So polymeric surfaces are exposed to environment during use. So what are the polymeric interfaces? There can be interfaces during processing in polymers in solution, right? So that were discussed. What is the interface region? So macromolecules in thin films. In case of very thin films, okay, so you cannot distinctly demarcate the bulk and the interface, right? Because it's very small, the film is, right? So and then surface energy of polymers, the interfacial energy, and how can you manipulate this. So these were discussed. Next lecture was on diffusion in polymers, so fixed law of diffusion, and then diffusion in liquids and crystalline solids. When you come to polymers, there is a mix of both, you can see, right? And then it's a combination of activated and free volume diffusion. And then what happens if you have a semi-crystalline polymer? What happens to the diffusion of small molecules? So obviously, crystallinity, it causes much more hindrance for diffusion of small molecules. So they have to take a detour, right, through the amorphous region, so that it can move from one place to another. It can diffuse from one place to another, right? Next, there was a discussion on compatibilizers. Compatibilizers for blends. What is the role and types of compatibilizers? Reactive compatibilization, and then fiber treatment and sizing. What are the natural fibers and polymers? Right? So these were discussed. The next lecture was on biopolymer application. So there was a discussion on xanthan gum, which has lot of interactions. Okay, the interaction plays the pivotal role in its application. And whereas in case of polyisoprene, which is your rubber, it's an ideal system where it is used as a here there is no interaction playing a role. It is only your segments, changing conformation, which helps in playing a role in as an elastomer and as in a vibration mount. Right? You're able to remember xanthan gum. You have your COH group,
Yeah.
OH group. You have your hydrogen bonding, right? All these things happens in case of xanthan gum. Next, the week 9 lectures were on adhesives and paints. So, what are structural adhesive, mechanism of adhesion, formula adhesive formulations. Okay, there was a discussion on paints as well. What are the components of paints, role of polymers in paints, and there was quite a bit of discussion on water-based paints also, which are associative thickeners. Next lecture was on dissolution and recovery. Right, mechanical. This is again sustainability. So here, what are the mechanical recycling processes and what are the challenges involved in mechanical recycling and chemical recycling? What are the different methods, right? And then there was a bit of discussion on dissolution and examples and recovery of solvent, dissolution rate, right? And what happens when an amorphous polymer is exposed to solvents? What are the different layers formed, right? And dissolution in amorphous polymers, and then what is the anomalous diffusion. So these were all discussed. Next set of lectures were on polymer processing and recycling techniques. So polymerization kinetics. was discussed, right? Polymer manufacturing, and then the reactive processing, polymer processing, composite processing, and three different types of polymerization. Your step growth, living polymerization, free radical polymerization were discussed in this lecture. Next lecture was on polymerization reactor. So your industrial polymerization, so bulk, solution polymerization, precipitation, suspension, emulsion, gas phase polymerization, and what are the different polymerization used in, what are the commercially available polymers like your LDPE, HDPE, polystyrene were discussed, and then some other examples of polymers and their processing polymerization techniques were discussed. Next lecture was on polymer processing. So, what are the unit operations involved in processing? What are the tools involved in processing? How was the flow behavior? Okay, liquid crystalline polyester was discussed. What is the milk flow index measurements? And then some dimensionless numbers which are very important in polymer processing. Your Deborah number, Weisenberg number, Reynolds number, right, and elasticity number. So these were discussed. Okay. And next again this lecture again was on polymer processing. So here your extrusion process and injection molding process were discussed in detail. The next lecture was again on polymer processing. What are the shaping operations? So extrusion dies, stretching, rolling, blowing operations, blow molding was discussed. What are the cycle time involved? Right, and production rate. So cycle time involved are very short time scales. That is why you have lot of production. That is why you have polymers becoming ubiquitous, and you see polymers everywhere. Right, your cost of production is very less because you know so many number of pieces can be produced in seconds. Right, and mixing in polymeric systems was discussed. Next, flow stimulation. What is the simulation? Sorry, continuum description, molecular description, right? So, a molecular description deals with solving your momentum balance, right? And then there was a discussion on mass, momentum, and energy balances, right? Yeah, for polymers. Okay, so this was discussed. The next lecture was on polymer processing for recycling. Okay, what is the primary recycling, secondary recycling, recovery and conversion? What is the targets in Indian national resource efficiency policies were discussed. Okay, operations before recycling. So before recycling itself, you have multiple operations involved. You have to sort them, right? So that you can recycle them properly and efficiently. The next lecture was on recycling, up down cycling. Okay, what are the challenges in waste handling? Right? Polymer processing, it's a complex transport phenomena. Right? What is upcycling? Okay, and mechanical chemical upcycling was discussed. Okay, upcycling through blending of polypropylene and LDPE was discussed. Next, this was again on recycle up down cycling. What are biocomposites? Twin screw extruder, polymerization and molding, where reaction and injection molding was discussed. Resin transfer molding was discussed, where a biocomposite sandwich structure was discussed. The next lecture was on flow behavior. So this was an introductory lecture on rheology, which was a concept based lecture. So what are polymeric fluid flow? So polymeric fluid flow is important as products also and during processing also. Right? For example, your ketchup has to come out of the bottle or the tube, right? So there, as an end product, the polymer has to flow, and it can't keep on flowing. Once it you have transferred to your, for example, on your bread, once you spread it, it should stay like that. So, how does a flow behavior, play an important role, right? So that was discussed, and non-Newtonian fluids, flow scenarios, and what is the response of the macromolecules. So these were discussed. The next lecture was on cross-linking. So cross-linkers for different polymeric systems, step growth and chain growth, and then extent of reaction for cross-linking in case of step growth polymerization was discussed. Cross-linking in rubber and its cure time. So there two trait test, oscillating disk and moving die rheometer was discussed, and cross-linking and gelation in terms of viscoelasticity was discussed. Right. Next lecture was on conversion of polymers. Right, conversion and Combustion of polymeric materials, your chemical recycling, the factors of affecting conversion, the rate of conversion, rate of absorption and diffusion. So chemolysis of PET and then conversion to feedstock. What is the combustion and incineration of polymeric materials? So these were all discussed in this lecture. Next lecture was on rheology and entanglement, right? So there was a discussion on shear and extensional flow, and then the rheometric geometries were discussed. So in your rheology, the basic study starts with having the system in one dimensional narrow gaps, and how do you control all the variables, okay? And how is the fiber orientation in case of shear and extensional flow, right? So these were all discussed. Then there was a discussion on rheological models. So linear viscous model, non-linear viscous model, which is a generalized Newtonian fluid, was discussed. Linear viscoelastic fluid. What are some shear thinning models were discussed, like your Carrier-Isuda model, Hershey-Bulkley model, Herschel-Bulkley model. And then there was discussion on non-linear viscoelasticity model also, your Pantheon-Tanner model, convected derivatives and frame indifference and material objectivity. So these terms were discussed. These terminologies were discussed. The next lecture was on rheology and processing. Right? You're able to follow, right? Both of you?
Yeah, yeah.
Okay, fine, good.
Yeah.
Yeah. You have to start recollecting because next we are going to start with some practice assignment also. So you should be answering. Now, so far I have spoken a lot. The next part you have to speak a lot. Okay? So then rheology and processing. So mixing in different flows. So for polymers predominantly you have your laminar mixing, right? Because of their high viscosity. Okay, what is a simple shear flow, right? Extensional flow, viscous dissipation, and then dye or extrudate swell was discussed. Okay, and then deformation in simple shear flow, your velocity gradient, strain rate tensor, stress tensor were discussed. Newtonian and generalized Newtonian fluid was discussed, right? And then different techniques of rheology, your rotational rheometry, tube flows, extensional rheometry, and then some trade test in rheometry were discussed. So the next lecture was on absorption and bleaching, right? What is the fate and this was on sustainability. So fate and transport of polymers in environment. So during as we know that you're throwing so people are throwing polymers into water bodies, and it's into all soil, water and everywhere. So obviously they may take up some material, they may absorb some material, they may leach out some material also, right? So what is the impact of those things? The thermodynamics involved in for example your solubility, partitioning, so option isotherms, and then absorption kinetics like Fickian, non-Fickian, and case 2 diffusions were discussed. Leaching and leaching kinetics was discussed. Right. The next lecture was on spelling of polymers, spelling of cross-linked systems. Right. So in case of your linear or just blanched polymers, the polymers in the presence of solvent, you know, they start slowly getting into the solvent and they will get solvated. Whereas for cross-linked systems, they take up solvent and they swell, right? And then osmotic pressure and chain elasticity, the balance between these two, the role in swelling, and then Flory-Rayner equation was discussed in detail, right? Next lecture was on viscosity for polymer processing. So your capillary rheometry was discussed, and then your Maxwell model uh, for viscosity was discussed with the sinusoidal input of strain rate. Then the final set of lectures, week 12 lectures, were on polymers and environment. So your microplastics, macroplastics, nanoplastics. So the fate and transport and how microplastics are present everywhere, including, you know, the digestive tracts of vertebrates and invertebrates. Also, you find microplastics prevalent. And then biodegradation of polymers, so which is very important in terms of sustainability. So degradation of polymers in environment, and then the concept of biodegradation was introduced. So it is not just if you see a bacteria growing on polymer surface, it does not mean it is getting biodegraded. It may be because of something that was absorbed on the surface, and because of that the bacterium is growing there. Okay, so not just the growth of bacteria, or any other microorganism can indicate there is a biodegradation process. So that was, explained. Next, biodegradable polymers. So polymers with biological relevance, and then what can be a degradation claim and what cannot be a degradation claim, right? And then there was a discussion on composting, right? And then biodegradation of polyhydroxybutyrate, polylactic acid, and what are starch-based polymeric systems was discussed. Then a final lecture of the course was again on biodegradable polymers. So application and processing. So most promising applications and what are the difficulties or challenges involved in using these biodegradable polymers, like your, for example, your starch or polyhydroxybutyrate or polylactic acid. Okay, what are the properties and what are the challenges involved in their usage? And then there was a discussion on biodegradable polyesters, your polybutylene succinate and butylene adipate terephthalate. Okay, and then biodegradable thermosets and elastomers. What about bringing biodegradability in terms of your elastomers and thermosets? For example, in epoxy, how can you produce it from kind of a renewable source like your vegetable oils and make use of those properties of triglycerides in vegetable oils to get a sustainable elastomers and thermosets. So this was discussed, and so these are the recap of all the week's lectures. Now let's get on to practice assignment session. Are you ready?
Yes, ma'am.
Okay, okay, both of you are ready. Now let's go through the first question. There are two different PTFE polymer specimens of the following density and percentage crystallinity. For PTFE specimen 1, the density is 144 gram per centimeter cube and percentage crystallinity is 50%. And for specimen 2, it is density is 2.215 and crystallinity is 75. Assuming the polymer is pure and defect free, the density of 100% amorphous PTFE will be, how to go about it? So these were all discussed in the particular week's practice assignment actually. How to go about it?
We will assume the density as one variable,
Okay.
and, we will connect the two equation. But how
Okay.
I will connect the equation? I don't.
What are the informations they have given?
They gave densities of two specimens and percentage crystallinity.
Okay. That means they are percentage crystallinity. If you see, one is 50 and other is 75. That means they are not 100% crystalline. So they have some
Yeah.
amorphous,
Yes.
part also and crystalline part also.
Yes.
Right.
Yes.
And they have given what is the total density. Right. So that means this total density will be related to the amorphous phase density and crystalline phase density. And they have given what is the fraction of crystalline phase also. Right.
But we can't just add the
Yeah.
densities of the amorphous and crystalline, right?
Yes, yes. That is why you have the fraction given, right? So how to proceed is that, uh, Revati, you want to comment something? You want to make a try?
Yeah, what is the actual density of, you're asking for density of 100% amorphous.
Yes, you are supposed to find out. So shall I proceed or do you want to think?
Yeah, you proceed.
Okay. So we have specimen 1 having density 2.144 and crystallinity 50%. That means the volume fraction of the crystalline phase is 0.5. Similarly, for specimen 2, you have the density given and crystallinity given. So, okay. So, there is a relationship between this volume fraction of the crystalline phase and your density of the total density and amorphous and crystalline phase density. Right? So, you have these three. So, where rho A is the density of amorphous phase and rho is C is the density of the crystalline phase. So, from this, you can incorporate for specimen 1 what are the knowns. So you have in case of specimen 1 you have the volume fraction known and your total density known and your amorphous phase and crystalline phase are unknown. So you keep it as such as equation 1. Similarly you can form an equation 2. So two equations are formed. So you have two unknowns, right? Your amorphous phase and crystalline phase are unknown, right? So you can just divide one by the other and then you just have to solve two equations. That's it. Divide one by the other, you will get this amorphous phase, and then you can also, so obviously if you divide one by the other, the crystalline phase, the denominator gets cancelled. So you will have the amorphous phase, right? Alone in the equation that can be solved and you will get what is the amorphous phase density, right? And if you incorporate into one of the specimens, then you will get this crystalline phase density also, right?
Yeah,
You're able to follow?
ma'am, can we do it like
Mm.
uh, as separate components? Like in this first specimen, can we write like density times volume fraction plus density times volume fraction equal to the total density? Can we do it like separate components?
Density, if you just rearrange this, you may not get as this, I guess, because your phi c into rho c minus phi c into rho a is equal to rho minus rho a, correct? So divided by, so you will have one more term of rho a there. So you can, so that is how you will get this formula. So this is the relation actually. Rho minus rho a by rho c minus rho a is your relation with the volume fraction.
Yeah.
Okay. Next. Now match the polymers to their families. So you have some family of polymers, you have COC double bond O group and then NHCOO group and then O C double bond O and CONH group. So you have to match which of these polymers they will have these kind of groups in them. You have set of polymers being given polyurethane, polyamide, polyether, polycarbonate, polyester.
First
So
one is polycarbonate,
okay,
polyurethane,
okay,
polyether,
okay,
polyester, polyamide.
okay. So, what about you, Paul? Do you agree with that, or you have a different?
Yeah,
Both of you agree.
the same answer.
Yeah, perfect. First is polycarbonate, then polyurethane, polyether, polyester, and polyamide. Very good. Next, radius of gyration gives an idea on the extent of macromolecule from its center of mass. Okay, for an ideal chain, radius of gyration is related to mean square end-to-end distance as. Is it related as Rg square is equal to R naught square by 4, or is it Rg square is equal to R naught square by 2, or is it Rg square is equal to 2 R naught square, or is it Rg square is equal to R naught square by 6, or is it Rg square is equal to 3 R naught square by 4 for ideal chain?
I think it's option C, but I am not sure.
Okay, What about you, Revati?
No idea.
Okay, now let's see the answer. It's actually rated as your radius of gyration Rg square is equal to R naught square by 6. Okay, this is how the relation is for ideal chain. Okay, and it's related to molecular masses, macromolecular size power 0.5 for ideal chain. Okay, next. Match the range of interaction for the type of non-bonded interactions. Charge, dipole, dispersion, charge, repulsion. The range of interaction 1 by r, 1 by r power 12, 1 by r square and 1 by r power 6. Just give it a try, both of you.
Um, Ma'am, I,
Ah, yeah.
for charge dipole, it's 1. For
Okay,
repulsion, it is 1 by R raised to 12.
okay,
For charge is 1 by R.
okay.
For dispersion, it is 1 by R square.
Mhm.
And for charge dipole, it is 1 by R to the power 6.
Okay. Okay, what about you, Revati? You have any idea? You want to give a try?
Uh, charge is 1 by R.
Okay,
Charge dipole is 1 by R square.
okay,
Repulsion is 1 by R per 6 and dispersion is 1 by R per 12.
okay,
Don't remember.
okay. Let's see. So, charge dipole is 1 by r square. Dispersion is 1 by r power 6. Charge is 1 by r. And repulsion is 1 by r power 12. Okay. So, this was discussed in this interactions, the non-covalent interactions, non-bonded interactions. Okay. Lecture. R is the distance between the interacting atom or macromolecule. Okay. Now, next. According to Stokes-Einstein relation, radius of gyration is directly proportional to the diffusion coefficient. Identify if the statement is true. Is it directly proportional to the diffusion coefficient?
True, but I'm not sure.
Okay.
Just give it a try.
Okay. What about you, Revati? Do you feel the statement is true?
Not sure.
It's true. Okay, it's actually false. So your Stokes-Einstein relation is the diffusion coefficient is inversely proportional to your radius of gyration. Okay. Okay. Next, two miscible polymers A and B are blended in weight ratio of 30 is to 70. If the glass transition temperature is Tg of the polymer A is minus 50 degrees and that of polymer B is 100 degrees, then Tg of the blend will be what relation you have to use?
Ma'am, the uh, Flory Fox.
Very good. So now what is the Flory-Fox relation?
Yeah, the T1 by phi 1 plus T2 by phi 2 equal to 1 by Tg.
Is it? Revati, do you agree?
I think it's the volume fraction by the glass transition of one component plus volume fraction by glass transition temperature of other component equal to 1 by the glass transition of the blend.
Okay. So do you agree, Revati?
I think 0.3 into 50 plus 0.7 into 100, not 100, 0.3x into 50 plus 0.7x into 100 is equal to 1. Can I equate it that way?
So one what Paul told us, right? You have to use Flory-Fox relation. So he said the Flory-Fox relation is 1 by Tg is equal to weight fraction of one polymer 1 by Tg of polymer 1 plus weight fraction of polymer 2 by Tg of polymer 2. Do you agree with that formula, or are you trying to say some different formula is going to get applicable here? Is it right what Paul told?
Uh, I really don't know. I need to revise.
Okay, fine. He was right actually. So your Flory-Fox relation is 1 by Tg is equal to weight fraction of 1 by Tg1 plus weight fraction of 2 by Tg2. So you have to incorporate weight fraction and glass transition temperature. Now another crux is that you have to incorporate the glass transition temperature in Kelvin. Okay. So once you have the formula, you have to also think of the units that are going to be used. Okay. So you have to convert the temperatures to Kelvin and then incorporate it. You will get the glass transition temperature of the plate. Okay. The rest is pure mathematics. So you will end up with a blend glass transition of 37.4 degrees centigrade. You're able to follow? Shall we proceed to the next question?
Yeah.
Okay, fine. Next question. A linear amorphous polymer has a glass transition of 10 degrees. At 28 degrees, it has a viscosity of 4 into 10 power 8 poise. The viscosity of the polymer at its Tg is dash into 10 power 13 poise. This is a gate question. So now, what relation are we supposed to use?
Ma'am, the uh, WLF,
Very good. Why do you say we have to use WLF? Why not uh, your Arrhenius?
because it is close to the glass transition.
Yes, they
When
are
they are
asking.
asking glass transition temperature,
Okay, okay, okay. So
but I forgot the relation.
yeah, that's okay. So you are right. So both the temperature glass transition is 10 degree, and they have given viscosity at 28 degree, which is closer to the glass transition temperature. So you have to use your WLF relation. So your WLF equation is log of eta by eta g is equal to minus of C1 into T minus Tg by T minus Tg minus C2. So these are all constants. So the value for this case is 17.44 and C2 is 51. So if you substitute all these, you have all other parameters, right? Except your viscosity at glass transition temperature, right? So another thing is that here you're using glass transition at direct temperature itself. Why do you think you're using direct temperature itself? Because you're just using the temperature difference. So whether it is going to be Kelvin or degree centigrade, the difference is going to be same, right? So
Mm,
once you
uh,
incorporate it, you will end up with the viscosity of glass transition is 1.295 into 10 power 13 points. Next.
Ma'am, how did you get C2 as 51 points.
These are constants. So for general materials, you will get this. It's for general polymers and all, you will get this. It's around C2 is around 50. It will be C1. You can also get it. Okay. So generally, they tend to give these values, or you can just go through some general values for polymers. Okay, in case they are asked in exams. Okay. So mostly, if these kind of constants are needed, they will be given. Okay, or some you will have, so for example, your C2 will be nearly 50. In fact, this was discussed in the lecture also. Okay, so you will have generally it is Tg minus 15, in one form. Okay, hope you got it. Right?
Yeah,
Shall I
yeah.
next? The size of a coiled polymer chain in a dilute solution is Rg in a good solvent, Ri in an ideal solvent, and Rp in a poor solvent. Select the correct ordering of the sizes. So you have a dilute polymer solution. Okay, and there are three different solvents in which the radius is given, the polymer size is given. In good solvent it is Rg, in ideal solvent it is Ri, and poor solvent it is Rp. Okay, so now you have to say which will have the highest size. Whether Rg will be greater than Ri will be greater than Rp, or Rg will be less than Ri will be less than Rp, or Rp will be greater than Rg will be greater than Ri, or Rp will be less than Rg will be less than Ri. Which one will be the right answer?
One
Um,
A.
Yeah, you're saying. So in good solvent, the polymer size will be highest, and then in ideal solvent, and then in poor solvent. Is it? So both of you agree?
yeah, good solvent, the radius will be higher.
Yes. Both of you are right. Because in good solvent, the polymer can have a expanded chain conformation. Okay. In poor solvent, it's more coiled conformation. In ideal solvent, it's called as theta condition, where there is no polymer and solvent interaction. The polymer behaves that there is nothing it is interacting with. Okay, and this is how is the polymer size in each of these solvents. Next question. Thermodynamically, two polymers with enthalpy of mixing delta H and entropy of mixing delta S form a miscible blend at a temperature T when delta H by delta S is equal to 0.5, or delta H by delta S is equal to T, or delta H by delta S is equal to 1.5 T, or delta H by delta S is equal to 2 times of P. Which one, under which condition you will form a miscible blend at temperature T?
Ma'am,
Hmm.
the miscible blend, the delta G is less than 0, but
Okay.
that is the only condition. But
Yes.
what is the condition with the H and S? No idea.
Okay. So, do you have any course on basic thermodynamics?
I just learned it in my TU, ma'am. That's all.
Okay, then obviously you must be having an idea that your Gibbs free energy change is related to your enthalpy and entropy. Okay. So
D.
which one? B you're saying. So your delta H by delta S should be equal to T you're saying. Is it?
Yeah.
Okay. How did you arrive at this?
Delta G is equal to delta H minus T delta S.
Yes, your
Delta
relation
G
is
is equal to 0. Delta H by delta S is equal to T.
So one part, what Paul said is right. One, the formula what you gave for Gibbs free energy change and how is it related to delta H and delta S is right. But both of you are missing one information. Let's see.
Miscible
So,
na 0.5. Yeah.
yes, yes, because as he said, your delta G of mixing should be less than 0. Okay. Then only you will form a miscible blend. So, delta G of mixing should be less than 0. That means delta H minus T delta S should be less than 0. So, delta H should be less than T delta S. So, delta H mixing by delta S mixing should be less than T. So, the only option given here which is less than T is your 0.5 T. So, obviously your delta H by delta S is equal to 0.5 T. Then you will have a miscible blend. Hope both of you got it.
Yeah.
Yeah, got it.
Okay, fine. Yeah. Secondary interactions are stronger with instantaneous initiation and propagation of crack in case of ductile polymers. Is it true or false?
True, but I am not sure.
Okay, what about you? Revati, do you think this statement is true?
It's false actually. If the secondary interaction is very good, I think cracking will not take place.
Okay. Uh, your answer is right, but your explanation to answer is not right. So, secondary interactions are strong with instantaneous initiation and propagation of crack in case of brittle polymers. So, your brittle polymers actually they have higher secondary interactions. Okay, and they tend to start propagating. Obviously, brittle means they crack easily, right? So, in case of brittle polymers only, you have your secondary interactions which are very strong with instantaneous crack propagation. Okay. Whereas in case of your ductile polymers, there is an yielding, that is, there is an orientation of macromolecules or crystals with large deformation depending on the plasticity. Okay. And there is an eventual failure also in case of ductile polymers. And finally, in case of flexible polymers, there are very weak secondary interactions. Right? For example, your rubber, your secondary interactions are very weak. Okay, that is why you consider them as ideal, right? Ideal systems. So here this stretching of segments is what is going to play a very critical role to large deformation with recovery on removal of load. Hope you got it, both of you.
Yeah,
Okay. Now next, compatibilizers decreases the interface thickness. Is it true? Does compatibilizer decrease the interface thickness?
true,
No, it increases.
true or
You want to say something, Paul?
nothing, ma'am.
Okay. Yes, you are right. It's false. It actually increases. The action of compatibilizer is that they increase the interface thickness. Right? For example, 4 to 60 mm. Okay. So there is much more, interactions and, uh, better interface and compatibilized. The system is the two polymers are compatibilized in that way by increasing the interface thickness. Glass fiber reinforced polypropylene composite is to be prepared with 20 volume percent of glass fiber. The density of glass fiber and polypropylene are 2540 kilogram per meter cube and 900 kilogram per meter cube respectively. The mass of glass fiber required to produce 1 kg of composite in kilogram is, what will be the mass of glass fiber to produce 1 kg of composite, where the volume fraction of glass fiber is 20 volume percent and density is for glass fiber it is 2540 and 900 kilogram per meter cube. This is a very repeated question in GATE. It has been asked in 2020, 2017, and 2010. So how do you proceed with this?
We'll initially assume the total volume as 100
Okay.
and calculate the mass.
Okay. So do you agree with that? Um, Revati, do you agree with that?
That is volume fraction of fiber into density of fiber divided by volume fraction of fiber, density of fiber, plus volume fraction of PP into density of PP.
PP. You're saying that way. Okay. Okay. Now let's see how to solve. So you have been given volume fraction. Okay. Of glass fiber 20%. That is nothing but 0.2. So and then your PP will be 1 minus 0.2, that is 0.8 is a volume fraction of polypropylene. So now you have the volume fractions. So addition of volume fraction will be 1. Okay. So you can assume the total volume of 1 meter cube. Again, Paul, as you said, you can also assume total volume as 100 meter cube. Okay. In that way also you can proceed. Okay. For simplistic approach, I am using 1 meter cube. Okay. The values
Okay.
will vary accordingly. So that means your here your volume of glass fiber will be, since I have assumed 1 meter cube, the volume of glass fiber will be 0.2 and PP will be 0.8. In your assumption, it will be 20 meter cube and 80 meter cube. And then you have the densities of glass fiber and this one. So density is so your mass of the glass fiber will be density into volume, and your mass of PP is density into volume in this case also. So, so the total mass will be, once you add these masses, you will get the total mass, and then the mass fraction will be the individual mass of the glass fiber by the total composite, uh, you know, mass. So that will give you what will be in 1 kg. Again, Revati, as you said, this is nothing but whatever you said. So your volume fraction or volume into density of the fiber by volume into density of the fiber plus volume into density of your
Yeah, yeah.
PP. Okay. So both of you are right in your approach. Slightly the numbers will start varying, but you will finally end up with the same number. Okay. Since in your case you said you will be using 100 meter cube, accordingly the numbers will slightly modify in the intermediate steps, but the final thing will be the same. Okay. Yeah, that's it. So 1 kg of composite will weigh this, will have this much of glass fiber. Next, for a polymer which follows the Markov-Wenck equation, the various parameters determined were as follows. They've given K is 1.2 into 10 power minus 4. Your eta is 2.4. A is 0.76. Okay. And they've also given Huggins constant as 0.33 and concentration C is equal to 0.3 gram per deciliter. This is a GATE 2008 question. They've asked what is the molecular weight of the polymer first, and the second part of the question is the specific viscosity of the above polymer. So how do you approach?
Eta is equal
We
to
will.
m to the power a.
Can you repeat it? Eta
That
is
is
equal to,
intrinsic viscosity is equal to k
hmm,
into molecular weight power a.
yes, that is your Markov-Wenck's equation. So do you have all the
Yeah, yeah.
parameters except the molecular weight?
Yes.
Yes. So then you can obviously calculate the molecular weight, right? Now for the next part of the question, how do you proceed? So your Markovitz equation.
Eta P by C is equal to eta plus Huggins constant into eta square C.
Okay. So that is your Huggins equation you're saying. Okay. So first let's discuss the Markovitz. As you said, it is eta is equal to k into m power a. So you have all other parameters except molecular weight. So if you substitute all the parameters, you will end up with molecular weight as 4.5 into 10 power 5. So now they have asked for specific viscosity. So your specific viscosity is given by your Huggins equation. It is specific viscosity by concentration is equal to eta plus Huggins constant into eta square into C. I think this is what you told, right?
Yeah, 0.89.
Yeah, perfect. So you can just substitute, all other parameters and then find out what is the specific viscosity, right? So hope both of you got it. So shall we proceed to the next question?
Yeah.
Okay. Dipole in PVC is on the dash, while in case of PEO it is along the dash. This you have to think on the macromolecular structure, the chemical structure.
The side chain and backbone.
Okay. So
Yeah,
what do you?
and backbone.
Yes, perfect. So in case of PVC, you have the side group is having the Cl, right? So there will be a dipole orientation because of C and Cl. Cl will be slightly more negative. And in case of PEO, it is along the oxygen is along the backbone. Okay. Yeah. Next, in D by relaxation model, as frequency tends to 0, then your E prime tends to dash and your E double prime is proportional to dash.
I have no idea.
Okay, what about you, Revati? You're able to recollect anything?
Mm,
Okay.
I think, yeah, you tell. No,
Okay. Okay. So your E prime is equal to your dominant polarization epsilon s, and your E double prime is proportional to omega. So this is your D by relation. Okay, the relaxation model. So as you substitute omega is equal to 0, then you will end up with this this term going 0. So you will have E infinity plus Es minus E infinity. So you will end up with epsilon s, and your epsilon double prime will be so this your here in the denominator it goes to 0, so you will have 1 in the denominator, so it is just directly proportional to omega, right? Now, yeah,
Yeah.
so it is okay. Now let's go to the next. The behavior of a polymer is described by Maxwell model, consisting of a spring element of modulus 10 power 10 Pascal in series with a dashpot of viscosity 10 power 12 pascals. In the solid, 50 seconds after sudden application of a fixed strain of 1%, the stress will be dash into 10 power 7 Pascal. So how do you do this? Any idea?
in series, stress will be constant. No, the in series, strain will be constant. Uh, stress will be constant. Then it's connected in series.
So you have to
Strain
use
will vary. Strain will vary.
they have said a fixed strain is applied. Now they are asking for what will be the stress for the entire system. It is not just for the spring or it is not just for the dashboard. So here they have said that the polymer is described by Maxwell model. So fixed strain is applied means what type of process it is? What is happening?
Stress relaxation.
Yes, very good. Okay. So now, so given polymer behavior follows Maxwell model. So this is how the Maxwell model is. So you have the spring and dashpot in series, and you said this stress is constant, right? Or you said strain is constant in series
It
Strain.
is constant.
strain is
Is
not
it
actually
being
constant. It is the stress which
stress
is
is constant.
stress which is constant. Okay, because this spring can have its own strain and it can expand to that possible extent, and similarly the dashboard have its own strain that to which it can expand. So your strain is actually varying between this spring and dashboard when they are connected in series. Okay, so this is the Maxwell model. Sigma plus lambda into dou sigma by dou t is equal to eta max into E dot. This is your Maxwell model. Okay, you have your modulus 10 power 10 pascals. Your eta is equal to 10 power 12 pascal seconds. That is your viscosity. They have given time and strain also they have given 1%. That is nothing but 1 by 100. That is equal to 0.01. So stress relaxation response. So the response for Maxwell model is sigma of t is equal to E max into E naught into exponential of minus t by lambda, where your E max is your modulus and your E naught is your strain. So since it is stress relaxation, obviously your strain is fixed. So it is 0.01. Okay, your lambda is your relaxation time. Alright. So relaxation time is given by eta by E from the given constants. You can calculate. Okay, so your lambda is equal to eta by E max. So it's 10 power 12 by 10 power 10. So it is 100 seconds. Okay, that is your lambda. And they have given T, which is 50 seconds. So after 50 seconds, what will be the stress? So it's just incorporating all the values given. So sigma at 50 seconds will be your E max, which is 10 power 10 into 0.01 into exponential of minus 50 by 100. You will end up with 6.06 into 10 power 7 Pascal. Hope you got it. Both of you got it?
Oh, yeah.
Okay, now let's proceed to the next question. The linear viscoelastic behavior of a polymer is described by Kelvin-White's model, consisting of spring element of elastic modulus 10 megapascal in parallel with a dashpot of viscosity 3.6 into 10 power 11 pascal seconds. A fixed stress of 40 megapascal is suddenly applied to a polymer and maintained thereafter. The value of the strain after 1 hour from the sudden application of stress is, so viscoelastic polymer behaves as Kelvin-White model. So now what are the things you can identify? Both of you, we just solved Maxwell model. Now you can get an idea on Kelvin-White model.
So Et is equal to sigma naught by E 1 minus E power minus T by lambda R.
That is your boy Kelvin-White model you're saying. Okay.
Yeah.
Okay. Now, Paul, you want to say something?
No idea, ma'am.
Okay. So you have your spring and dashpot in parallel. So in this case, your stress will be taken up different stresses will be taken up by spring and dashpot, but your strain will be the
Strain
same.
will be constant. Yeah.
Yes, yes, and this is a this is a creep experiment where you are
Experiment.
applying a constant stress. Okay, they've given the modulus of spring and viscosity of dashpot, and then they've given fixed stress what is being applied. So Kelvin model is given by, so your strain at any point of time t is equal to sigma naught by E into 1 minus epsilon, sorry, exponential of minus T by lambda r. Okay, so your lambda r is eta by E. So from this you can find out what is your lambda r in seconds, and then after 1 hour of stress application they have asked. So E at 1 hour, that is nothing but 3600 seconds. So you have all other parameters except your strain at 3600 seconds. So once you substitute all the parameters, you will get strain as after 1 hour, it is 0.3808. Okay, hope you got it. Both of you got it. Shall we proceed to the next?
Yeah.
Okay. You have any other doubt?
I have a doubt
No, no, ma'am.
actually. How is your exam pattern going to be? How much percentage of marks will be getting from assignment questions and how much from this problem solving discussion?
The problem solving session, this is just to give you an idea of the concept and brushing up of the concept. Not exactly from the problem solving session, the questions will be taken up. Okay, this is to give you an idea. Okay, so your exam will be based on whatever concept lectures that was discussed in the course. Okay, it will not be like a percentage of question from your assignment questions and percentage of questions from your practice assignment question. Practice assignment sessions is just to help you out to refresh the concept, and also when you're solving the assignment problems and all, not to help you out. For that purpose is this session, and to reinforce the concepts, right? You will start thinking of the concept much more clearly and all. Okay, I cannot say that questions will be asked from this exactly, but they may also ask, because many of the questions I asked is from gate, so they may also take from gate. Okay, so I'm not sure about that. Okay, but this practice assignment sessions are for you to learn basically, so that any question asked on Kelvin Moid model, you can remember, okay, Kelvin Moid model, these are the conditions and this is how the equation will be. Okay, and this is used for the response is used for creep response. The creep response was solved for Kelvin White model. Okay, so these kind of things you can just recollect. Okay, to reiterate that this practice assignment sessions are basically for. Okay, next, because these the questions for for this session I'm taking it from the course only. For example, your concept based questions and all, like your whatever I give as fill in the blanks or multiple choices and all, are from directly from the lectures only, and I take also gate questions which are related to the lecture. Okay, hope you got it. You got it. Can I proceed to the next question?
Yeah, sure, ma'am.
Yeah, Deborah number is the ratio of dash. When Deborah number is very much less than 1, then relaxation process would lead to dash.
Ratio of retardation time by experiment time.
Is it retardation time?
Relaxation time, sorry.
Okay, okay. So if the if D if Deborah number is very much smaller than 1, then relaxation process would lead to what?
Discuss.
Okay, let's see. Do you want to say anything, Paul?
Relaxation process will lead to damping,
Yes,
but I'm not
but
sure.
okay. So it is relaxation time by experimental time, as you said. So so when Deborah number is very much smaller than 1, that means your relaxation time is very small, or you're giving ample experimental time. That means, as you said, it can be more of a viscous nature, right? That means, what is viscous nature all about? It is about dissipation of energy. So the material is able to relax well, and it is able to, sorry, the material is able to dissipate energy. Okay. So lambda tends to 0, or it can be either lambda tends to 0, instantaneous relaxation, or it can be experimental time, you're giving an ample amount of time. So both of these leads to dissipation of energy. Okay. Next, formed polymers have dash thermal conductivity than normal polymers. Higher, lower, similar, or none of the above?
Lower.
Lower thermal conductivity. What about you, Paul? Do you agree with that?
Yeah, ma'am. I agree.
Yes. Formed polymers have lower thermal conductivity. In fact, one order lower thermal conductivity, because thermal conductivity of polymers in the range of zero point 0.1 to zero point 0.6 watt per meter Kelvin. For formed polymers, it's 0.01 to 0.08. So one order lower. Next, for mechanical analog elements, in parallel, dash is equal. Just now you said, when we were discussing on Maxwell model and Kelvin model, you were saying whether it will be stress or strain, or stress and strain, or neither of them, when the mechanical analogs are in parallel.
Strain,
Okay. What about you?
strain is
Revati, do you agree? Do you agree with that?
One second, one second.
Okay. Take your time.
Actually, what is the question? Analog animals in parallel dash is
So
equal to
when mechanical, we have seen spring
dash for
element.
the spring and all.
Yes, yes. When these
When it's
elements are
parallel, strain is constant.
strain is constant.
Dash,
Yes, both of you are right. So when these elements are arranged in parallel, the strain is constant. When they are arranged in series, then stress is constant. Okay. Yeah. Next question. The following figure shows scales of hardness for different class of materials. Okay. They have shown, shore A, shore D, and Rockwell hardness values for elastomers, thermoplastics, thermosets, and thermoplastic elastomers. Now you have to state true or false. Higher the numbers on these scales imply higher hardness. Is it true?
yeah.
false. I think it's false, but I'm not sure.
Why do you say it is false? Say, for example,
Because
shore A,
elastomers have low hardness.
see, for example, shore A, okay, let's take shore A hardness. If shore A hardness, a material with shore A hardness 20 will have a higher hardness, or material with shore A hardness 100 will have higher hardness.
Sure, 100. Yeah.
Yeah, that means the statement is true, right?
Yes, ma'am. Yes.
Okay. Next, elastomer of shore A hardness of 30 has higher modulus than elastomer with shore A hardness of 90. Is it true?
False. False.
How do you say so?
Modulus is stress by strain. And actually, when the hardness is more, the modulus should be higher.
Yes, hardness is more, modulus is higher. So the statement is true.
I mistook
Sorry,
the
sorry, sorry, sorry,
statement.
sorry, sorry, sorry. You are right. The statement is false. So The statement is false. Yeah, sorry. Uh, when the hardness is lower, the modulus is lower. When the hardness is higher, the modulus is higher. Okay, it gives just an idea that modulus will be higher or lower, but it is not that hardness 30 means the modulus will be 30 Pascal. Okay, because these are trade tests. Hope you got it, both of you. You're right, Revati.
Yeah.
Shore hardness of 30 has higher modulus than 90 is a false statement. Shore hardness 30 will have a lower modulus than shore hardness 90. Okay, now let's proceed to the next question. Identify if the statement is true in the case of polymer composites. Ease of processing increases with the size of fiber. As a fiber length is higher, the processing of this composite, polymer composite with this fiber will be easier. Is it true?
False.
False.
Yes, both of you are right. So the ease of processing decreases with the increase in size of fiber. So if you start having long fibers, then what happens is, how do these fibers, long fibers orient, and how do they flow? So these all become questions. The fibers will get and they will get entangled. They may get entangled. So the viscosity will go to higher values. So due to these complications, the processing of longer and longer fibers becomes challenging. Next, ductile polymers are characterized by, what is the key prominent feature of ductile polymers? How do you identify a ductile polymer is ductile from a stress strain curve?
Yielding.
They'll have yield stress.
Yielding. So the ductile
Yielding.
polymers are have yielding. Okay, this is the yield point. Okay, yeah, both of you are right. Next, phenomenon of polymers undergoing plastic or viscoelastic deformation till failure during cyclic loading, usually less than the strength of the polymer. Is it fracture, or is it impact, or is it fatigue, or is it plasticity?
Fatigue.
Fatigue.
Yes, both of you are right. It's fatigue. The number of cycles to failure dash with increase in stress amplitude. So does it increases or does it decreases, or is it independent of stress amplitude, or is it increases initially and then decreases?
Decreases.
It
Decrease.
decreases. Yes, both of you are right. So as the stress amplitude increase, the number of cycles to failure, it decreases. Okay, this is the fatigue or endurance limit. Next, in suspension polymerization, wide distribution of monomer droplet leads to dash molar mass distribution.
Increase. Molar mass distribution.
You have to say whether it will be broad or narrow.
Broad.
Broad.
Yeah, it will have broad molar mass distribution, because in case of suspension polymerization, the monomer droplet is the reactor actually. So if the droplet size varies, widely, then each droplet will create a polymer of a particular molar mass. So since droplet distribution is high, size distribution is high, the molar mass distribution will also be high. Next, you have to match. Okay, there are certain processing steps and there are certain items. So you have to match these: rotational molding, extrusion, reaction injection molding, blow molding. So, and then the items given are polyurethane, use of gas, centrifugal force, and twin screw. Which of these matches with what?
Reaction injection molding polyurethane.
Okay,
Blow molding, rotational molding centrifugal force.
okay,
Blow molding use of gas.
okay,
Extrusion twin screw.
okay. What about you, Paul? Do you agree with her?
Yeah, I agree.
Yeah, perfect. So rotational molding, it uses centrifugal force. Extrusion, you have twin screw extruder. Reaction injection molding is commonly used in polyurethane, and blow molding uses a gas. Perfect. Now next. Viscosity of LDPE increases from 2000 to 13,000 Pascal seconds after 100 cycles of recycling. What causes this? What happens that leads to this? What happens in LDPE
Cross
during?
linking.
Huh?
Cross linking.
Cross-linking.
Perfect. Cross-linking reaction can take place in LDPE that leads to increase in molar mass, that leads to increase in viscosity. Perfect. Now identify the viscous dissipation term in the below equation. So you have the equation, you have the energy balance equation, rho Cp dou T by dou T plus rho into V dot grad T and then Kt into
Second
this.
term, rho V grad T.
That is what you say viscous dissipation term, is it?
Yeah.
Both of you agree?
I don't know.
Okay. It is actually the last term is what your viscous dissipation. It's nothing but your stress and strain relation, right? So, because your grad V is nothing but your gradient of viscosity multiplied by strain. So this is what it gives your viscous dissipation. Okay, the this second term it's actually convection. It's actually velocity into gradient of temperature. This is a temperature gradient, and velocity is because the molecules are moving. So the molecule is convected. The heat is convected.
Yeah, yeah. Sorry, sorry.
Yeah, no problem. You all learned, right? All of us learned. Okay. Okay. Now let's go on to the next question. Identify which type of flow, shear or extension has a better mixing from the below figure. So you have specific energy and then after in the y-axis and after deformation by area of hypothetical sphere before deformation. And you have the curves. In case of simple shear, you have a straight line with a continuous increasing line, whereas in case of uniaxial and by a planar extension, uh, the specific energy increases initially and then it becomes almost constant. So, which type of flow will be better? Whether it will be simple shear or whether it will be shear or extension.
Here I think.
Say shear. What about you, Paul? Do you agree with her?
No, I don't know.
Okay. It is actually extension flow has better mixing because in extension flow you could see that the specific energy required so for the deformation to happen is lesser, right?
Yes. Yeah.
Whereas in case of simple shear it continuously requires a lot of energy, right? More energy compared to your uh, simple shear. Okay. Hope Paul you also got this point. Shall we proceed to the next question? Both of you, are you there? Shall we
And
proceed?
Fine.
Yeah.
can you
Yeah.
repeat it once more?
Okay.
How it is?
Yeah. See, for example, so area of after deformation means, so after material starts deforming, there will be an area change, there will be an area increase. So, for example, if you just look into 10 power 2 as area after deformation, so and then compare the energy. If you just draw, horizontal line to the specific energy, you could see that in case of uniaxial extension or biaxial extension, the energy required is less, right? Whereas if you look into simple shear for the same amount of deformation, it requires much more energy, right? So here
Okay.
deformation means so material has to deform or move from one point to another for mixing to take place. So for the same amount of movement, shear takes more energy than extension. That means extension is a better way of mixing, right? Because we have to consume minimum energy for doing any process, right? Energy conservation should be there. You have to conserve,
Okay.
save energy, right? So in terms of energy perspective, you could identify that extension has a better mixing. Okay.
Okay.
Yeah. Now next, identify if the statement is true or false. As the interaction parameter chi becomes more negative, the swelling ratio decreases. Is it true?
True.
What about you, Paul? Do you agree?
No, no idea.
It's actually false. Actually, if chi becomes, the interaction becomes more and more, parameter becomes more and more negative means there is,
Sorry, sorry. I thought more. I thought it is positive. I did not see the word negative.
negative. Okay, okay, okay. So if interaction parameter is more negative, then there is much more favorable interaction between the solvent and the polymer, cross-linked polymer system. So it can take up much and much more solvent. So the swelling ratio will be higher and higher. So this is always the relationship. Okay. Now next. Petro-based polymers are all non-biodegradable. Is it true or false? Are all petroleum-based polymers
False.
non-biodegradable? False. What about?
False.
Okay, good. Can you name a petro-based polymer which is biodegradable?
Polyvinyl alcohol.
Very good. Yes. So, as you said, it's false. So, not all petro-based polymers are non-biodegradable. Polyvinyl alcohol is a petro-based polymer, but it is biodegradable. It is having a it's a water-soluble polymer as well. So, it can be degraded because of the hydroxyl group which is present, and because of the macromolecular activity, chain scission happens, and eventually it gets assimilated and mineralized. Another example is your polycaprolactone. I think this was asked in your week 12 assignment question.
Yes, ma'am.
Yeah.
Well asked.
Now, next, the final question for the session. Polyhydroxybutyrate is brittle in nature. Identify the key challenge in application of polyhydroxybutyrate based on the discussion in lecture 87, and also related to the brittle nature based on stress strain curves. So what does the statement say? Well, it says that polyhydroxybutyrate is brittle in nature. Okay. And lecture 87, which was discussing on the biodegradable polymers, there was a discussion on polyhydroxybutyrate, in which there was a discussion on challenges involved in usage of polyhydroxybutyrate. One challenge was that large scale production. The large scale production is a challenge because it is from a microbial source. So obviously your yield will be very less. So large scale production is a challenge. There was another challenge related to its property that was discussed. So what is that property, and how does that property look in a stress strain curve, and how is it related to brittle nature? This is what is the question. In fact, this was discussed in last week's live session.
Processability.
Yes, but there is a difficulty in processing due or it's more into the property than processability. It's more into the property of the polyhydroxybutyrate.
I don't know, ma'am.
Okay, you want to give a try, Revati?
Transparency and toughness.
Okay, you got it.
It's little difficult, no? Because it is brittle, we need to improve the toughness.
Yes. So brittle polymers will have lower toughness, right?
Yeah.
Yes, yes, that's what you got it. So the brittleness of polyhydroxybutyrate is this is because the brittleness is because of large crystalline domains in the form of spherulite in PHB. Okay, and the key challenge in polyhydroxybutyrate is toughness, transparency, and toughness. So toughness. So now toughness is the energy absorbed before failure, which is given by area under stress strain curve. So in case of brittle polymers, you could see that the area under stress strain curve is very small, right? So that is where your brittleness shows lower toughness. So your brittleness in the polymer has actually impacted your toughness of the polymer, and which is in fact due to the large crystalline domains in PHP. Okay, hope you got it, both of you.
Yeah.
Okay, that's it with the session. Now, any other doubts? Hope you got some idea. I just brushed through whatever
Ma'am,
concepts. Yeah, tell
when
me.
I went through one solution, uh, I don't know which weeks, but I found one question. The polymer blend is similar to that of block copolymer, but I didn't understand how it is.
Okay. See, in case of polymer
Because
blends,
one,
you will have what you will have is that you will have a it's a blend of two polymers, polymer A and polymer B, right? So you will have some A rich domains and B rich domains, right? In case of
yes,
blends, okay. So this is similar to your copolymer. How is it similar? In copolymer, what you will have? You will have A block followed by B block.
yeah, yes, ma'am.
So this is the equivalence. Okay, that is what was
But when we mix the polymers, they will get interchanged, right? There is no block separation.
no. See, it depends on complete miscibility and the miscibility level of the polymer. Okay, so that is why you may have a rich phase and B rich phase. So which you can in case of blends. Okay. So in that case, you will see that this A block can, A rich phase can be said as A block, and B rich phase can be said as B block. So this is what is a copolymer and this kind of blend analogy. Hope you got it.
Okay,
You are able to follow, right?
yeah, yeah.
Because polymer miscibility, again, not all polymers are 100% completely miscible. So depending on the miscibility, so partially miscible cases and all, you may have some A rich phase and A lean phase and B rich phase. Okay, so that can be imagined as a block, very similar to your block copolymers. So A block and B block. Okay, any other doubts?
Actually, next week, 24th, they have given a cyclone alert. I'm in Chennai.
Oh,
If there
okay.
is any of such reasons, what about the exam?
I am really not sure. You have to check with the NPTEL team. Okay. Uh, you have to check with the NPTEL team based on, your.
Because this week was very bad, last 2, 3 days.
Yeah, 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 yeah.
The same
Uh,
thing happens next week because they've said 24th and our exam is on 26th. And our
okay,
centers are also at a place where there is waterlogging.
okay. So maybe you can just check with the NPTEL team. See if it is going to be cyclone and all, they will just give some alternate arrangement also. Probably. Because this we cannot control, right? It is nature's this one. So
Yeah, that
based
is
on
what.
based on
Because
it, some.
having done the whole thing, if you are unable to take up the exam, it will become a big issue.
Yeah, just check with the NPTEL team. They will definitely, make some alternate arrangements and all. So just check with the NPTEL team. You can just ask NPTEL team, mail to them, and then they'll get back to you accordingly. Okay?
Okay. Thank you.
Yes.
Thank you.
Yeah. So any other doubts?
No, ma'am.
No other doubts. Hope this session was useful. So, go through the lectures well, prepare well for the exams. Not only for the exams, but for understanding polymers, just go through the lectures, have a feel of it. Okay, because the lectures are designed very beautifully, the slides and everything, the concepts, so make use of all these lectures. Okay, as a fundamental study of polymers. All the best for your exams.
Thank you.
Okay, so if there are no other doubts, we can officially close the session. All the best.
Thank you. Thank you.
Happy weekend.
Thank you. Bye.
Bye
You too,
bye.
ma'am.
Thank you.
And thank you very much. Your summaries and all were very helpful, ma'am.
Thank you. Thank you so
Sessions
much.
and all.
Thank
Yeah.
you. All the best.
Thank you,
Thank
ma'am.
you. Actually, I really appreciate your this one because sometimes I find that there are no this viewers. In spite of that, you take full strain to take because actually I like to attend every week, but
Hmm.
every Saturday became a working day for us.
Oh, okay, okay, okay.
Okay.
Oh,
Today
okay.
itself it is a working day because it was the last session I took leave. Otherwise, I'd be in travel during the
Oh,
session.
okay, okay. No, for some people, if it is working day, it's an issue. For some people,
Mhm.
if it is holiday, it's an issue because you have this holiday mood that,
Because no, if it is for other course which I was doing, actually 6 to 8 it was. That was better. I reach
oh,
home and after that we have the session.
oh,
Here
okay, okay.
it is the traveling time for us. That is the problem.
Oh, okay, okay, okay.
Anyway, thank you very much. I've
Yeah.
gone through all your sessions after coming.
Okay, okay.
Thank
Nice,
you. Thank
nice,
you.
nice. Thank you. Thank you for your support. Thank you all.
Bye.
Bye bye.
Bye.